Hi, welcome to your MECH 200 Statics online classes. In this video, we'll continue through the topics of Chapter 4, in which we are going to study the different aspects of force system resultants. I hope you enjoyed this class. So far, we've been discussing the concept of the moment of a force and how to calculate its magnitude using the scalar formulation. However, as we saw in the previous video, the moment is a vector quantity, just like the force, which we can also represent using the Cartesian vector notation. But before we continue our conversation about moment calculation, let's first expand our knowledge of vector algebra and introduce the cross product between two vectors. Just like the dot product, the cross product is another method of multiplication between two vectors and mathematically represented by this formula, in which we read it as C equals to A cross B. The magnitude of the vector C is defined as the product of the magnitudes of A and B and the sine of the angle theta between the tails, if theta is between 0 and 180 degrees. Graphically, we can also use the right-hand rule to show the cross product between the A and B by curling the fingers of the right hand from vector A to vector B, in which vector C points in the direction of the thumb. If we also take a unit vector UC defining the direction of C, then we can expand the mathematical expression of the cross product to this formula here, in terms of the magnitude of the vector C. Likewise, the dot product. The cross product also follows the same laws of multiplication operations, such as the associative law and the distributive law. However, the commutative law is not valid, and we're going to see this in detail next. The vector equation provided in the previous slide can be used to find the cross product of any pair of Cartesian vectors, including the Cartesian unit vectors as shown here in this picture. For example, if we want to find the product I cross j, then we have to apply that equation and find the magnitude of the resultant vector to be 1 times 1 times 1, which results to 1. For the direction, we can get it from the right-hand rule, and the resultant vector of I cross j points towards the positive k direction. This method can be visualized more easily considering this figure here. This circle connects all unit vectors and shows the rotation directions following the curved rotation of the fingers of the right hand to facilitate the calculation of the cross product. For a counterclockwise rotation, we have a positive sign for the resultant vector, and for a clockwise rotation, we have a negative sign. For example, if we take the same cross product calculated earlier, we have that the fingers of the right hand will rotate counterclockwise from I to j, and the cross product will result into plus k, or positive k. We can do the same thing for I cross k, in which now the arrow rotates towards the clockwise direction, and the result is minus j. For I cross I, we have no rotation, and then the cross product is 0. Going further for all other possible cross product combinations for the unit vectors, we build this table here, which will facilitate a lot the calculation of the cross product for any pair of Cartesian vectors. Let's consider now the cross product of two general Cartesian vectors A and B. Based on the table we just built, we can express the cross product of these two vectors using this compact form here, in which we just have to expand this determinant. Here is how we are going to do it. For example, for the I component, we first reduce the 3 by 3 determinant to a 2 by 2 determinant by striking through the row and column of the I element. Next, we have to take the product j cross k, which according to our table results to positive I. Then we have to multiply the two elements of the main diagonal of the reduced 2 by 2 determinant, subtract from it the product of the elements of the secondary diagonal, and take this result as the Cartesian component of the cross product in the I direction. For the j component, we basically do the same thing. First, reducing the determinant by striking through the row and column of the j element, and then taking the product I cross k, which results to negative j. You should never forget this negative sign here. Then next, we multiply the elements of the main diagonal of the reduced determinant, subtract from it the product of the elements of the secondary diagonal, and this will be the Cartesian component of the cross product in the j direction. And finally, we repeat the process for the k component. Strike through the row and column of the k element, take the product I cross j, which results to positive k, multiply the elements of the main diagonal, subtract from it the product of the elements of the secondary diagonal, get the Cartesian component of the cross product in the k direction, and this is the general equation for the Cartesian vector representation of A cross B. Now that we've got enough mathematical background on the cross product between two vectors, let's transfer these concepts to the vector formulation of the moment of a force. In general terms, the moment of the force F about the point O is defined as the cross product between the force vector and the position vector directed from O to any point on the line of action of the force. This vector representation of the moment as a resultant of a cross product operation can be seen in this figure. We can see here that the angle theta between the position vector R and the force vector F plays a major role on the definition of the moment arm D. With this in mind, the magnitude of the moment can be defined by this formulation here. Another important property of the moment, which can be easily explored using the cross product operation, is what we call the principle of transmissibility of a force. This happens because F can be applied at any point along its line of action, and it still creates the same moment about the point O. In other words, we don't need to care about which position vector we should consider to calculate the moment, as long as it connects the center of rotation O and the line of action of the force. The application of this principle is very convenient when we are solving 3D problems. We can go further and expand the Cartesian formulation for the cross product we developed earlier to a generic position and force vectors to calculate the moment. To do so, we need first to establish a coordinate system x, y, and z in which the position vector r and the force vector f can be expressed as Cartesian vectors. Then we can calculate the moment by solving this determinant equation, which, when expanded following the same procedure presented in slide number 4, leads to this general formulation for the Cartesian vector representation of the moment. And finally, if a body is acted upon by a system of 3D forces, the resultant moment about point O can be determined by the vector addition of the moment generated by each force. This resultant can be written in terms of the cross product of the position vectors and the force vectors according to this equation here. Now it's time to work on one example. In example 4.3, we have two forces acting at points A and B on the rod shown in this figure. And we have to determine the resultant moment that those two forces create about the flange at point O. Furthermore, we need to express this resultant moment as a Cartesian vector. Since we're dealing with a 3D problem, the best way to solve it is using the Cartesian notation. Then, we start with the vector equation to calculate the resultant moment, which involves the position vectors of the points of the application of each force. For this task, we consider the distances given in the figure, and we easily get the position vectors of point A and B in the Cartesian vector notation. Then, going back to the resultant moment equation, we just expand it and use the components of the position and force vectors in the determinant notation here. By solving the determinant, we get the general Cartesian vector expression, which after the solution of each element, we have this final answer for the Cartesian vector notation of the resultant moment. And with that, we are done with the second part of Chapter 4. Thanks for watching, and I'll see you in the next video.